covered our year 11 content. We now have enough time to get through all of our year 12 content. We're going to look at bivariate data analysis, which is scatter plots, the correlation coefficient, the line of best fit, and the least squares line of best fit. And we're also going to look at normal distribution, which is the properties. We're going to look at the properties of normal distribution, and we're going to talk about z-scores and interpreting z-scores. The first thing I wanted to draw your attention to is stats has a whole section on the formula sheet. All of this stuff is related to normal distribution, the whole section. So this section is covered on the summary sheet, but you need to know what it actually means. Okay, scatter plots. Scatter plots are used to determine the relationship between two numerical variables. So in completing bivariate data analysis, we'll collect data for two different variables and then we display it in a table. So we might look at somebody's height and weight, and then we determine, is there a relationship present between those two variables? Then we determine, are they independent or dependent variables? Is it a strong relationship? We can answer a bunch of questions. This is what a scatter plot looks like. It is an axis, a vertical and a horizontal with a bunch of dots. Each dot represents a piece of information. So this one is like almost 4-4. So to describe patterns, we're going to use 4 different pieces of information. Is it positive linear, negative linear, non-linear, or no correlation? So if there's a linear relationship, the dots will approximately be in a straight line. So see how here the dots are it's pretty hard to miss that they're going up in a positive manner. There is a positive linear relationship. This is a non-linear relationship because there's no straight line. If there are a bunch of dots in here as well, it would still be non-linear. As long as no line is created that goes in any direction, it is going to be non-linear. Now this is a positive linear pattern because the dots are generally going from the bottom left to the top right. This is a negative linear pattern because the dots are generally going from the top left to the bottom right. Just like how this would be a positive gradient and this would be a negative gradient. So this is no correlation because there is no way to draw a line or to put a curve in that represents these dots. No correlation. This is non-linear pattern because there seems to be some correlation, but it is nowhere near being a straight line. So once we've established if it's a positive, negative, non-linear, or no correlation, we then describe the strength. So we add a second term in. So it's positive something, negative something. It can be strong, moderate, or weak. Strong correlation is where the dots are very much centered together. Moderate is where you could probably draw a nice large sized rectangle around them. And weak is when it's very weak that they're headed in the same direction. If we only had a couple dots up here and up here, we would say no correlation. But because it generally appears that they're headed in this direction, it's a very weak one, we still say there's a weak correlation. So example question, what is the strength of the linear relationship displayed below? I'm going to give you about 20 seconds to pop it in the chat. Okay, first thing you want to look at, is it strong, weak, or no correlation? I'm going to say it's strong because the dots are all very much close together. Is it a positive, negative? It's going to be a positive because the correlation is headed from the bottom left to the top right. So it's a strong positive correlation. Here's an example question. The table below compares a father's height and his daughter's height in centimeters measured over 10 years. Draw a scatter plot to represent this data. Describe the correlation between these two variables. So let's have a look at our solutions. The first thing I would do is label each axis. So the father's height is going to be our independent variable because he is the one who is just changing on his own. The question is the daughter's height dependent on the father's? So we're going to draw out equal intervals, 155 plus 2.5 plus 2.5. So we're going with plus 2.5 as our intervals for the father. Now the daughter grows a lot more, so we're going to go with intervals of 10 for her. So once we've drawn that out, I'm going to give you guys a second. We're then going to talk about how we plot our dots. Okay, I know that it's not enough time for you guys to draw that on, but I need to keep moving and keep you guys, I don't want to give you any silence for too long. How do we draw a dot? So let's have a look here. Father's height 157, daughter's height 95. This would be 157 for the father and 95 for the daughter. So we draw a dot there. We're going to continue drawing on our dots until we filled in all, how many data points did we have? All 10 of our data points. Now we need to figure out if there's a correlation. So let's see, all of our data goes in this direction, right? So it's going to be positive. And I would say that it's generally quite a strong correlation. So we would say strong positive correlation. As the father's height increases, so does his daughter's height. However, once the father reaches his maximum height, this becomes stagnant. Now, there's a much better way to describe the strength of correlation without having to depend on words. We can actually just use a number. Now, this is called the correlation coefficient. You might also see it be called the Pearson's correlation coefficient, but it's called the correlation coefficient. What is the correlation coefficient? So to quantify the strength of a linear association, so i.e. if we're determining a number which represents the strength of the relationship between two variables, we're going to use Pearson's correlation coefficient. Now here's a really confusing bit. You would hope that it's using the letter C or P. No. Pearson's correlation coefficient is demonstrated by the letter R. So Pearson's correlation coefficient is R. Now, when you go into your calculator, and we'll talk about this in a sec, you have a mode button. Mode 2, stats. 2, you then go into 2 plus 2, which is A plus BX. You will have the option to hit shift 1.5 when you need, sorry, this is going to make more sense in a second. In your calculator, when you go to a certain screen, it says 3R. R in your calculator is Pearson's correlation coefficient. So it's not just on your exam or on your paper. Your calculator, if you're using the correct one for the HSC, will have 3R for Pearson's correlation coefficient. So the correlation coefficient, to explain a little bit further, is a range. So let's imagine we have a little graph, a little bar here. This is perfect positive. This is a straight line positive. This is perfect negative, straight line negative. This is 0, where nothing is correlated to each other. This is 0.5, where things are getting pretty close. And this is negative 0.5, where things are getting fairly close as we go down. It can be perfect positive, perfect negative, or anywhere in between. Basically, the closer you get to 0, the closer you are to no correlation. The further away you get, the closer you are to perfect correlation, perfect negative or perfect positive. So we're going to use this table as a guide of how to describe it, because not only do you need to use the table, but you need to use the words associated with each number to describe correlation. So you can't just drop the whole strong, moderate, weak thing. You're going to use the number and the word strong, moderate, weak. So it could be a strong positive correlation, which would mean it's between 0.8 to 1. Moderate positive would be 0.5 to 0.8. Weak positive would be 0.3 to 0.5, and no correlation will be 0 to 0.3. A strong negative will be negative 0.8 to negative 1. A moderate negative will be negative 0.5 to negative 0.8. A weak negative will be negative 0.3 to negative 0.5. And no correlation will be negative 0, or will be 0 to negative 0.3. So here's a key point. You are only expected to do this via our beautiful calculators. There is no way for you to use the Pearson's correlation coefficient without using a calculator to work it out. They are not expecting you to be able to do that. In fact, they're not going to teach you how to do that because it's very, very complicated. So we need to note the meaning of the relationships. If it's positive correlation between two things, it means that both things increase or decrease at the same time. Both of the people's heights go up at the same time. both of the weights go down at the same time. Both of the cars drive at the same speed, whatever it is. There is an increase or decrease at the same time between both variables. If there is no correlation or zero correlation, there is no relationship between the variables. So as this person's height increases, this person's weight stays stagnant. There is no correlation. If there's a negative correlation, one variable increases while the other variable decreases. My weight goes up as my amount of food intake goes down. There's a negative correlation there. Okay, this is the bit we're going to take a minute on to get you guys very much understanding this. To calculate the correlation coefficient given a data set, first things first, screenshot this, but I'm going to show you how to do it on your calculator. Okay, I know it's a bit hard to see, but follow these steps. Number one, hit on. Blank screen on your calculator. I'm not kidding you guys. This is something you need to know for your final exam. If you do not know this, you will fail this question. They are not going to give you instructions. You cannot carry these results or these steps into the exam. On. Okay, mode. Mode on my calculator is next to on. I don't know where it is on yours. It should be around the top. Mode. Then you're going to hit, you'll see 3 options. 1 comp, 2 stat, 3 verif. You're going to hit 2 for stat. You're going to get a bunch of different options. Number 2 should be A plus BX. You're going to hit 2. You should get something that looks like this. 2 columns, X, Y, and a bunch of 1, 2, 3. You can put data in. This is where you put your data in. Let's say X is the height of a person and B is the weight of the person. I'm going to put 3 pieces of data in. I'm going to put the height of 180 equals, sign to enter it, a weight of 60. I'm going to put, you fill out one column first. So 180, and the next height is going to be 160, and the next height is going to be 140. Then I'm going to move with my little button here. I'm going to move myself over to the other column and put myself in the first position so I can fill in the data. I'm going to say the weight of this person is 70, the next weight is 60, the next weight is 50. Now I have 3 pieces of data in my 2 columns. Now I'm just going to hit on. The data is still in there. It's chilling in the calculator, but we're going to hit on or AC, whatever you want to hit. Now I'm going to hit AC shift 1. I've hit AC shift 1. I have type data sum var reg min max. I'm going to hit 5 for reg. This means regression, regression. 5. Now I have 1 is A, 2 is B, 3 is R, 4 is X, and 5 is Y. I'm going to hit 3 to get the Pearson's correlation coefficient. It's going to say R. I'm going to hit equal 1. I had perfect correlation between my 2 variables. Okay, we're going to do that one more time. Put your calculator, hit mode, go back to 1. Mode 1. I'm going to give you guys a second. Okay, one more time. Mode. We're going to hit mode. 2 for stats. 2 for A plus BX. We're going to have some data. I want you to do the following. X is 190 equals 170 equals 150 equals. Take your cursor or your little controller, move it to the top of the Y column. I want you to do 60 equals 40 equals 20 equals. I want you to hit on or AC. I want you to hit shift 1, 5 for regression, 3 for correlation coefficient, equals 1. Perfect positive correlation. Okay, 20 seconds, screenshot that. Put your calculator back to the base of stats mode. Once you've got all your answers, you just hit on and then go back to mode 2, 2, and you go back to your little table. Okay, example question. A teacher measured her students' heart rate in an examination and their height in centimeters and presented the information in a table. Calculate the value of the correlation coefficient correct to 4 decimal places. All right, so heart rate is going to be our X. Height is going to be our H, our Y. So let's get our calculators out, get our little tables. Okay, 61. You're going to hit 61 equals 63 equals 63 equals 67 equals 69 equals 71 equals 72 equals 75 equals 78 equals. So now we have 9 pieces of information sitting in our little X column. We're going to move our little cursor over to the Y column, pop it to the top. Now we're going to write down our height. 154 after everyone you hit equals. 172, 151, 163, 180, 165, 168, 170, 158. An important thing to double check is that your data is ending in the same line. So you shouldn't have one extra X or one extra Y. I'm going to give you guys 10 seconds to catch up. Have all your data entered, and I want you to hit on or AC. Okay, once you've done that, we're going to do shift or on or off or hit on or AC, one of the two buttons. Shift 1, 5 for regression, and you should get R equals 0.25556 for blah, 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 right there. The solution to the closest 4 decimal places is 0.2556. We have to round up the 5 because it was 25556, which means we round that up to a 6. Okay, I think you guys should be following. I went through that nice and slow. We're going to move on to line of best fit. So after drawing a scatter plot, using the value of the ordered pairs, we can now draw a line of best fit. If the points have a linear correlation, we can approximate a straight line graph that relates the two variables. Now, this is called linear regression. The aim of the linear regression is to model what that line would look like if we used our point-intercept formula, which is our gradient intercept y equals mx plus c. So before we draw a line of best fit, we need some form of data. So we use these points to guesstimate a line, and then that's our line of best fit. Use the points below, draw a scatter plot and a line of best fit. So 0, 6, 224, 339, 444, 559, 664, 779, 884. We've plotted all of those in. These were our y, these were our x. These all been plotted in. As we can see, the points do not exactly line up. So therefore, we're going to draw a line of best fit. So students often find this quite hard to do. The line should pass through as many points as possible. And if it doesn't pass directly through a point, you put the same number of points on either side of the line. So 2 above, 2 below, and it passes through 4. So let's have a look at this line of best fit. It passes through 1, 2, 3 points. And there are 1, 2, 3 points below and 1, 2, 3 points above. They're very close to the line, but there's 3 below and 3 above. So if we go back to this question, we would want to draw our line and see how in this one it doesn't have to start from 0. We'd want to draw our line something like, and this is very hard to do straight on a computer, something like this. So we have, okay, it'd probably be better going a bit down this way, but you can understand it's hard to do. But we would try and go through maybe this point, this point, this point, and this point, and then we've got 2 below, or we'd have, 2 above, 2 below if we try and get through these points. It's very hard to do. I would recommend having some practice on paper. It's very hard to do on a computer, I'm saying, but you just have to make sure you have the same number below and the same number above, and as many through the line as possible. We now need to learn about least squares line of best fit. This is quite complicated. It's the least squares line of best fit formula. It represents the straight line equation when it's trying to find that formula. We just use y equals mx plus c. But it only requires us to do it using our calculators. In order to find the line, we must use the given data set, so the height and weight or whatever it was, and a particular statistics mode to calculate the gradient and the y-intercept. So we're going to do this equation. Let's go back to our calculators. Let's hit on, mode 2, 2. We have our little table. Sorry, sometimes I have to throw my calculator to get the screen to show up. I've had this one since year 7, which was 2015. I was in year 7. So it's almost 10 years old. Okay, so we're going to add in our heights first. 150, 152, 155, 160, 165, 167, 169. Move our cursor over to Y, to the top of Y. 25 equals 23 equals 28, 26, 30, 29, 27. We added all of that in. Just hit AC or on. Now we go to, we enter our data. We go AC, we go shift 1, and then we go 5 for regression. We have 5 different options. Now, we need to find what B equals because B is our gradient and A is our y-intercept. So our formula looks like y equals bx plus A. So the gradient is B. So we're going to hit 2 for B equals. Now B should equal for you 0.22. I have 0.22, 0.465, 8902, 0.22. Now I'm going to get back to on, shift 1, 5 for regression. I'm going to hit 1 for A equals, and I got A equals negative 8.354409,318. So negative 8.35. Now I have that. We're going to use our least squares line of best fit for y equals mx plus c. So we're going to put in y was our foot length and h was our height. So we're going to change them to their actual measurements. 0.22 was our b, which is our gradient, and negative 8.35 was our y-intercept. So now we have a formula where we can answer questions. What is the expected foot length of a student given that their height is 180 centimeters? So 180 is our height. We plug it into 0.22, 180 minus 8.35, 31.25 centimeters for a foot length. Okay, we're going to have a look at normal distribution before we finish up. We haven't got too much longer left, guys. Really good job so far. In a normal distribution, the distribution of data is symmetrical about the mean. So let's just kind of backtrack. We have something in data called the mean, right? The mean is the average, the mean, median, mode, all of that stuff represents the average, the middle, the most popular, what's happening at the middle of our data. Normal distribution, which is pictured on our formula sheet, is if you have normal, mathematically normal distribution of data, the most normal way it could be distributed. The mean and median are approximately equal, and a bell-shaped curve is going to represent normal distribution. So this is what it looks like. It's based on something called the empirical rule. So what this is based on is another concept called Z-scores. So you have to understand these Z-scores. When we look at normal distribution, 0 is the mean. So if the mean in any given score is 10, the average age of a person in the football team is 10. Well, let's say the age goes up by 6 months. So this is 10.5, this is 9.5. 34% of people will be somewhere between -1 and 0 Z-score. 34% of people will be between 0 and 1 Z-score. So 68% of data will generally be between -1 and 1, which is 1 standard deviation above the mean and 1 standard deviation below the mean. So Z-scores are representing a number of standard deviations away from the mean. If you're not following, it's okay. You'll have plenty of time to revise this, but in the interest of time, I'm just going to use the words that you should understand or should try and understand by now. If you haven't covered it in class yet, that's fine, you will cover this. If you have, hopefully this is jogging your memory. These are the empirical rules. 68% of data will be between -1 and 1. 95% of data will then be between -2 and 2. 99.7% of data will be between -3 and 3. Only an extra 0.15% is either side of +3 or -3. Now, on your formula sheet, you get the graph of Z-scores, and it says approximately 68% of scores have Z-scores between -1 and 1. Approximately 95% of scores have Z-scores between -2 and 2. Approximately 99.7% of scores have Z-scores between -3 and 3. Now, you have to remember that breaks down into 34, 34, 13.5, 2.35, 0.15. I would recommend that as soon as you get in the exam, you write them on and you remember them for that formula sheet. The empirical rule is aiming to help you remember the percentages. So the rule is also known as 68, 95, 99.7. So if you remember those three numbers, you should be okay. You can always remember that you've got to halve them as well. So 34, 13.5, 2.35, and 0.15. Okay, so what is a Z-score? A Z-score, which is a standardized score, is a tool of comparison in a normal distribution. So it is the number of standard deviations that the score is from the mean. So to calculate the Z-score, we use the score minus the mean over the standard deviation. So say I got a 50 on my maths exam. That's my score. The mean was a 45 and the standard deviation was a 5. 50 minus 45 over 5 gives me 1. I was 1 standard deviation above the mean, which means my Z-score is 1, positive 1. So on this graph, I would be here. Now, we can also flip this formula around. I think I go through this with you, but if I don't, we can flip this formula around to find our score by rearranging the formula. So how would we do that? If we want to find our score, we're going to times both sides by standard deviation to get it on its own. So Z-score times standard deviation equals my score minus the mean. And I'm going to add the mean to the other side to get it on its own. So Z-score times standard deviation plus the mean equals my score. The heights of Year 12 girls are normally distributed with a mean of 165 centimeters and a standard deviation of 5.5 centimeters. What is the Z-score for a height of 154 centimeters? Okay, so Z-score equals my score minus the mean over the standard deviation. My score was 154 centimeters. The mean was 165 centimeters. The standard deviation, 5.5. Now this is an important note. If you need to go back to stats mode, hit mode 1 for comp. Then you're going to hit fraction. 154 minus 165 over 5.5. I have a standard deviation of -2. This means I am 2 standard deviations below the mean. Okay, and a Z-score of 0 means your score is equal to the mean. A Z-score of 1 is your 1 standard deviation above the mean. A Z-score of -1 is your 1 standard deviation below the mean. The larger the Z-score, the further it is from the mean of the data. So this applies to both negative and positive. Think of your correlation coefficient. The further you get from 0, the more perfect it becomes. The further you get from a 0 Z-score, the further you're getting from the mean. So we're going to do a question. After sitting an exam, a university student is told they have a Z-score of 0. The marks in the test were normally distributed with a mean of 65.5 and a standard deviation of 4.8. What mark did the student achieve? Now, because they have a score of 0, we don't actually have to work it out. We just know the mean was 65.5. They had a score of 0, a Z-score of 0. They got the mark 65.5. But for the sake of it, let's do the question. Z-score equals their mark was 65.5. The mean was 65.5. And there was a standard deviation of 4.8. 65.5 minus 65.5 over 4.8, we get 0. We can also rejig our formula and check that we're right by going the Z-score is 0 times the standard deviation, which was 4.8, minus the mean, which is 65.5, and make sure we put our brackets in. And we should get, unless we've rearranged our formula incorrectly, you should get 0 if you put it in correctly. Yes, okay. So 65.5, we need to move that out of the way. Willow is in year 11 and has completed 3 out of 4 English assessment tasks. A summary of her results is shown below. What is her Z score in task 3? Okay, her mark in task 1 was 15, her mark in task 2 was 24, her mark in task 3 was 19. The mean of task 1 was 14, she had a standard deviation of 3. The mean in task 2, we don't know, and she had a standard deviation of 4. The mean in task 3 was 23, she had a standard deviation of 2. Her Z score is going to be her score, 19, times, oh, I'm forgetting my formula, hang on. 19 minus the mean, which was 23, standard deviation over 2. So we go 19 minus 23 over 2, and we get a Z score of -2. -2. We can also use Z scores to compare scores that are in the same data set. So when we have 2 Z scores, we then compare them against the mean. The HSC marks for standard maths are normally distributed. This is always our key, normally distributed. Mean of 67, which is a Z score of 0, standard deviation of 7. Zach's mark was 94. Barbara's Z score was 3. She's claiming she got a higher mark. So is her calculation, or is her claim correct? So let's find out what Zach's Z score was, and then we can figure out who had the higher mark. So Zach's Z score is going to be his mark, 94, minus the mean of 67, over a standard deviation of 7. 94 minus 67 over 7 is 3.85, which means he had a Z score of 3.85. Now, because it's a positive and it's higher than 3, Barbara's claim is not correct. So we did this by finding Zach's Z score. We could also do this the other way around by finding Barbara's score. So we know she got a score of 3, the mean was 67, and the standard deviation is 7. We then need to find her score. So we rearrange our formula, 21, so we do 7 times 3, 21 equals x minus 67. We add 67 to both sides, x equals 88. So her score in the exam was 88, but Zach's score was 94. Now this was the 2020 HSC question that was on my exam. It was quite hard, so I'm going to show you the working out here instead. Okay, the intelligence quotient scores for adults in City A are normally distributed with a mean of 108 and a standard deviation of 10. So we need to find the first thing, well, I'll read you the question first and I'll explain what we're doing. The IQ score for adults in City B are normally distributed with a mean of 112 and a standard deviation of 16. So the first thing we're going to do is find our 2 Z scores. So City A Z score is going to be x minus 108 over 10. A City B Z score is going to be x minus 112 over 16. Simon, who lives in City A, moves to City B. The Z score corresponding to his IQ score in A is the same as the Z score corresponding to his IQ score in City B, which means that these two x's have to equal the same thing. So we're going to form an equation. X minus 108 over 10 has to equal x minus 112 over 16. So we're going to turn it into 2 equations by going 10x minus 112, which is going on this side, and then 16x minus 108. And we're going to create 2 equations. And now we just need to move each part of the equation over. So we subtract 1120 from 1728, 608. We get 6x and we subtract 10 from 16x. 6x equals 608. X equals 101.3. So Simon's IQ had to be 101.3. Now it is a little tricky to grasp. So I'm going to go back, have a look at the question again. First Z score for City A. Z score equals score minus 108, standard deviation of 10. Second Z score, score minus 112, standard deviation of 16. If you can put together those 2 formulas, you're on the right track. I wouldn't be as concerned about answering the question because it is quite difficult and you just need to be able to answer it by the HSC. But as long as you can put together those 2 equations, you should be able to move forward with the question.